Let's start with last chapter of your fourth module, that is IPv4 addresses. Every device will have a logical address. That logical address is known as IP address. There are two versions of IP address. IP address with a version 4, that is IPv4, and IP address with a version 6, that is IPv6. In this we are going to study about the IPv4. IPv4 address is made up of 32-bit address, and this address is unique and universal. There are some terminologies to be studied in IPv4 addresses. We'll study the terminology. The first terminology is address space. The meaning of address space is nothing but the total number of addresses used by a protocol. Let us understand what you mean by address space. If address contains n bits, then total number of addresses those can be generated is 2 raised to n. That 2 raised to n address generated is nothing but the address space. Similarly, here you can observe in IPv4 it is made up of 32 bits. Hence, n value of the IPv4 will be equal to 32 and address space of the IPv4 is 2 raised to 32. This is regarding the address space. Then as a second terminology we have about the notations. IPv4 addresses can be represented in two notations. One is binary notation and second one is dotted decimal notation. In binary notation, the address is displayed as 32 bits, which are grouped as 4 bytes, where each byte is made up of 8 bits. You can consider the example. In the example, you can see 4 different colors. Each color will represent each byte. Now, the second one is dotted decimal representation. To make IPv4 address more compact and easy to read, we have this type of address notation. It is very simple. What we have done, we have converted the binary numbers into decimal numbers and each decimal number is separated by dot operator. It is nothing but dotted decimal notation of IPv4 address. Now, the next concept we are going to study about the classful addresses. Address space is divided into 5 different classes: class A, class B, class C, class D and class E. And the meaning of this is IP address space or IPv4 address space is distributed among these 5 classes. To find which type of address we are using or to find address belongs to which type of class, we have the following table. You can just observe the table. In the table there are two notations, binary notation and dotted decimal notation. First let us consider the binary notation. In a given address, we need to observe only the first byte of the address. In first byte of the address, if first bit is 0, then it belongs to class of the type A. If first two bits are 1 and 0, it is of the type class B. If the bits are 1, 1, 0, it belongs to class C. If the bits are 1, 1, 1, 0, it belongs to class D. If the bits are 4 ones, it belongs to class E. In the same manner, we have dotted decimal notation. Again here also we are observing the first byte itself. If the range of value in a first byte is 0 to 127, then it is class A. 128 to 191, class B. 192 to 223, class C. 224 to 239, class D. 240 to 255, class E. We'll explain this concept by taking the example. You can consider this example. Find the class of each address. Now can you guess which type of notation we have? We have the notation dotted decimal. Now to find which type of address, we are going to observe the first byte. So in the A question, the first byte is 227. For that you can just refer this table. Where the 227 belongs to, it belongs to class D. hence it is of the type class D. Then we have 193, again sorry, you can just refer this 193, it belongs to class C, hence you have class C. Then you have 14, 14 belongs to class A, it is of the type class A. You have 252, it belongs to class E. In the same manner we have about the binary. Again we are going to observe only first byte, starting bit is 0, so no class is starting with a 0, it belongs to class A. Next bit is 1, so there are 4 possibilities, so we need to observe next bit, again it is 1, we have 1 1, there are 3 possibilities, again observe next one, it is 0, there is only one possibility, class C, hence it belongs to class C. Then for the C, 1 you have 4 possibilities, next bit is 0, only one possibility, that is class B. Then you have 1, so there are 3 possibilities, again you have 1, 3 possibilities, again you have 1, there are 2 possibilities, again the fourth bit is 1, then it belongs to class C. Now we'll study the next terminology, net ID and host ID. Only the class A, class B and class C are divided into net ID and host ID. Length of net ID and length of host ID varies based on the type of class they use. Again, to study the net ID and host ID, you can refer the diagram. Each class is made up of 4 bytes, total of 32 bits. So in the class A, the first byte is considered as net ID, all remaining bytes are host ID. In class B, first 2 bytes represent net ID, next 2 or last 2 bytes represent host ID. In class C, first 3 bytes represent net ID and last byte represent host ID. Then we have the next term as mask. Mask is used to find or it is used to calculate net ID and host ID. Mask is of 32-bit length. First n bits in the mask will be continuous 1, then remaining, that is 32 minus n bits, will be continuous 0. When you consider a class A, then n value will be equal to 8 bits. So n value is always equal to bits of net ID. Then for class B, n value is 16. For class C, n value is 24. The meaning is, in class A, first 8 bits are ones and remaining 24 bits are zeros. In class B, first 16 bits are 1 and remaining 16 bits are zeros. In class C, first 24 bits are 1 and remaining 8 bits are 0. Same thing we have represented here. In class A, first 8 bits are 1, remaining all 24 bits are 0. So when you have all 8 bits as 1, its decimal representation or decimal equivalent is 255 dot, next byte is 0, next byte 0, next byte 0. In class B, 16 bits are continuous 1, which is equal to 2 bytes. So decimal equivalent is 255.255, remaining 2 bytes are 0. In class C, 24 bits are continuous 1, where 24 bits is equal to 3 byte. Decimal equivalent is 255.255.255 and last byte is 0. Then we have the concept called subnetting. Now we'll study what you mean by subnetting. Network is divided into smaller network. Those smaller networks are known as subnetworks, and each subnetwork have their own address, which is in the form of subnet ID and host ID. It is similar to that of networks, where we had network ID and host ID. Here we are dividing the network into subnetworks. Hence we have, instead of network ID, we have the subnet ID. Then host ID remains the same. And this subnetting is mainly applicable to class A or class B. We'll explain this subnetting by taking the diagram. You can just observe the diagram. There are n number of machines, machine A, machine B, up to machine n. All those machines or nodes are connected to switch, then switch is connected to router, router to other networks or the internet. Now this is a larger network. This larger network is assigned with the address 141.14.0.0. Again, which type of address it is 141? To check which type of address it is, you can just observe the table. We have the starting byte as 141. Where the 141 lies? It lies at the class B. Hence, there we have taken the example of class B. Now, we have bar 16. The meaning of 16 is nothing but the network ID. And in this network, we can have 2 raised to 16 hosts. So what we did? We have divided the whole network into 4 subnetworks. You can observe 4 rectangle box. Each rectangle box consists of various machines. This is nothing but the subnetworking. And each subnetwork has its own address. So first subnetwork 141.14.0.0. Second one 141.14.64. Third one 141.14.128. Last one 141.14.192.0. Bar 18. Later we'll see how we got that 18. Now all these 4 subnetworks are connected using their private router. That private router is known as site router. From site router, it is connected to router, then to the internet. Now, let us see how we got this 18. In the first diagram, the whole network diagram, we had bar 16, where that 16 was representing network ID. In the same manner, this 18 represents subnetwork ID. To calculate that, we have the formula. You can observe the formula here. N sub equal to small n plus log s to the base 2. Where this n sub is nothing but length of the subnet ID. Small n is length of the network ID. And the term s is nothing but number of subnets. So we'll replace the value. Length of the network ID is 16 plus. Here they have mentioned it as 16. It is nothing but network ID. So that is the length of net ID plus log. S stands for number of subnetworks. We have divided into 4 subnetworks. We got the value 18. That 18 is nothing but the subnet ID. Now, initially what was the mask address of class B? It was 255.255.0.0. Again, this mask address we already studied. You can just see here. Class B. In class B, first 16 bits were continuous 1 and next 16 bits were continuous 0. Their decimal representation was 255.255.0.0. This was nothing but the mask value of class B. Now, after subnetting, the mask value changes. How it changes? Since in this diagram we got subnet ID as 18, the meaning of subnet ID is, or the meaning is, subnetwork is again made up of subnet ID and host ID. So subnet ID in the sense continuous 1, host ID is continuous 0. Since we got the value as 18, there are 18 continuous 1s, then remaining 14 are continuous 0s. According to that, first byte all 1s, second byte all 1s, in third byte, instead of having all 1s, what we have? First 2 1s and remaining as 0, last one is 0. So decimal representation of first byte is 255, second byte is 255, decimal representation of third byte is 192, and last one is 0. Here the subnet changed. So initially in the mask there were 16 ones and here there are 18 ones. So in subnetworking, number of ones increases. Now, the next topic is regarding the supernetting. Supernetting is just the reverse of subnetting, and supernetting is applicable to class C, where several class C blocks are combined to create large range of addresses. In subnetting, we were dividing the blocks of class A or class B, and in supernetting we are combining the blocks of class C. And in subnetting, number of ones were increasing, it is just reverse of that. Here number of ones decreases, and there we had a formula to calculate subnet id as n of sub equal to n plus log s to the base 2. And here we have the formula to calculate supernet id as n super equal to n minus log c to the base 2, where C stands for number of class C blocks combined. There S was standing for number of blocks of subnetting, and there also N stands for length of net ID. Here also N stands for length of net ID. To explain both subnet and supernetting, you can just consider this example. Initially they have taken the class B default mask address. Class B has a mask address as 24 ones and 8 zeros. Now if we break this network into 8 subnets, then to calculate subnet ID we have n, that is length of the subnet ID, plus log the blocks we divided. So the length of the subnet ID is nothing but number of ones. Totally we have 24 number of ones, 24 plus S stands for 8 subnets, log 8 to the base 2. We get the subnet ID as 27. That is 27 ones in a subnet mask. Initially we had 24, and after subnetting we'll have 27 ones, increase in the number of ones. Now we'll apply this for supernetting. In supernetting, instead of breaking, we are going to combine 8 classes of C to form the supernet. Now n value is 24 minus log 8 to the base 2 will get 21. So in the supernet mask there are 21 ones and remaining 11 are zeros. So here number of ones decreases. This is about supernetting and subnetting.